In the discussion on static measurement of mass we mentioned weighing scales. Now we present the measuring instruments of mass and weight in more detail. While scales and balances are both used as weighing devices, their intended purposes slightly vary. Scale measures weight whereas a balance measures mass. However, many balances are now used like scales to measure the weight of an object. Based on their working principle, there are two main classes of weighing scales, mechanical and digital. Mechanical weighing scales operate using a system of springs or levers. Spring scales and hanging scales measure weight based on the deformation of a spring due to the load. The weight of the object causes the spring to compress or stretch, and this deformation is measured to determine the weight. These scales are known for their mechanical simplicity but may lack the precision. Balance beam scales and trip scales are weighing instruments based on Archimedes' law of the lever stating that a lever is in balance if the total torque acting on its left-hand side is equal to the total torque acting on its right-hand side. Analytical balances are extremely precise and are used to measure very small amounts of substances in labs. Digital weighing scales or balances utilize electronic components and sensors for weight measurement. They convert the force exerted by the object into an electrical signal, which is then displayed as a weight reading on a digital screen. Electronic weighing instruments can be simple digital scales or hanging scales, but their most sophisticated versions like analytical balances are used in laboratories. Digital analytical balances are generally more accurate and precise than their mechanical counterparts. Weighing devices used for commercial or laboratory use are often designated within accuracy classes based on the number of scale divisions. Scales in the first accuracy class are ideal for precision lab work, and have a minimum of 50,000 divisions. They display results in increments of 1 mg or better. Semi-micro and analytical balances are often rated class first. In the second accuracy class, scales have up to 100,000 divisions. Typical uses of scales in this class include laboratory weighing, weighing of precious metals and gems, and grain test scales. The third accuracy class can be divided 3 categories: medium, large and ordinary. Scales in the medium category are designed for industrial or commercial use and they have a maximum of 10,000 divisions. Scales in the large category are also used for commercial use, but they offer a much larger capacity. They also have a maximum of 10,000 divisions. Ordinary scales in the third accuracy class are used to weight heavy load but have up only to 1,200 divisions. Now we will discuss the operation of various balances and scales where we mainly focus on mechanical instruments using the lever principle. We start with the mechanical analytical balance. An analytical balance is a measuring instrument used to determine the mass of small samples with a high degree of accuracy and precision. A mechanical version of such a balance is depicted in the figure. Its main component is a central balance beam with a sharp steel knife edge attached to the beam. The axis of rotation of the beam is determined by the contact points of the knife edge and the top of the central pillar of the device on which the edge is balanced. 2 knife edges turned upside down are balanced on both the ends of the central beam, where the axes of rotation of the knife edges can be adjusted by balancing screws. Each of the knife edges is connected to a hook in a stirrup. Bows with pans of equal masses are suspended from these hooks and can rotate about the 3 horizontal axes of rotation determined by the contact points of the 3 knife wedges. A pointer attached to the central knife wedge rotating in the front of a scale on the central pillar is used to determine the equilibrium state of the device. In order to protect the sharp edges from being bumped and the balance from disturbance, the pans can be arrested and released between measurements. The horizontal position of the balance platform can be adjusted by the leveling screws supporting the platform, and a plumb line is used to indicate when the balance is level. The analytical balance is enclosed in a glazed weighing chamber protecting the device from airflow and temperature fluctuation. Since the minimum weight is usually 1 mg in the standard weight sets, 2-pan balances are equipped with a rider made of thin wire. The variable seating of a rider on the rider bar enables smaller increments of mass than the available minimum mass to be added to the pan. Let us consider a balance with equal weights on both its pans in static equilibrium. If extra mass is added to the weight on one of the pans, then the excessive load will rotate the central beam of the balance indicated by the pointer moving in the front of the scale. The greater the angle of deflection of the pointer is produced by a given excessive load, the greater the sensitivity of the weighing balance is. The sensitivity of the balance can be described by the ratio of the angle of deflection of the pointer to the extra mass placed on the pan, or the ratio of the displacement of the pointer over the scale to the extra mass. Let us suppose that the axes of rotation determined by the positions of the 3 knife edges lie in a plane, that is the points of rotation O1, O and O2 lie on the same line, and the 2 arms of the balance have the same length L. Let G0 and C denote the weight and the center of mass of the central beam and the pointer without the pans. The total weight of a pan and the body placed on each pan is denoted by G. For a complete symmetry of this setup, the center of mass C must lie on the vertical line passing through the point of rotation O in a stable equilibrium where the point O is above the point C with the distance d between them. If extra mass is placed on the right pan producing the excess of weight delta G applied on the right-hand side arm of the balance, then the central beam with the pointer will rotate through an angle phi and reach a new equilibrium state. Since the lever principle tells us that the torques produced for both the arms are balanced for any angle phi in equilibrium, the vector sum of the torques must vanish. The figure shows that the torque produced by the extra weight delta G with respect to the point O is given by the magnitude of delta G times the length L of the lever arm times cosine phi. Similarly, the torque produced by the weight G0 acting at the center of mass C with respect to the point O is equal to minus the magnitude of G0, times the distance d times sine phi. Then the balance equation tells us that the sum of these two expressions is equal to 0, and we can express tangent phi from this equation as the ratio of delta G times L to G0 times d. Since the extra weight delta G can be written as the extra mass m times the gravitational acceleration G, and the weight G0 as the mass m0 of the central beam and the pointer without the pans times the gravitational acceleration G, tangent phi is equal to the ratio of m times G times L to m0 times G times d, or simply as the ratio of m times L to m0 times d. For very small extra mass used in practice, the angle of rotation phi is also small and tangent phi can be approximated by phi. As a result, we can express the sensitivity given by the angle of deflection phi divided by the extra mass m as the ratio of the arms L of the balance to the mass m0 times the distance d, that is the sensitivity of an analytical balance is proportional to the length of its arms, and inversely proportional to the mass of its central bar and the distance between the axis of rotation of the bar and the center of mass of the bar. In fact, the points of rotation O1, O and O2 do not necessarily lie on a line. Therefore the sensitivity of the balance also depends on the load, and it decreases with increasing load. Now we describe how to read an analytical balance. When the balance pans are arrested, we place the sample of unknown mass on one of the pans and the sum of the weights of the weight set of known mass on the other pan. After the pans are released, the balance performs oscillations about an equilibrium position determined by the loads on the pans, which has a small damping factor due to the small friction. In order to reduce the measurement time and increase the precision of weighing, the equilibrium position is determined from the oscillation based on the theory of harmonic motion. The deflection of the pointer on the scale is read off at an arbitrary odd number of adjacent turning points after the pointer passed through the first 3 to 5 turning points. Then we take the average of the values at the left and the right turning points separately, and take the average of these two averages. For example, if the values read off are x1, x2 and x3 for 3 adjacent turning points, then the result x of the measurement is given by 1/2, times the average of the first and the third values plus the second value, that is 1/2 times the sum of x1 and x3/2, plus x2. We have seen that classical analytical balances are equal arm balances, where the torque produced by the weight of the sample on one side of the balance and the torque produced by an adjustable known weight on the other side cancel each other out in equilibrium. Then we can determine the mass of the sample from the deflection of the pointer of the balance and the known weight used for the measurement. Modern electronic laboratory balances operate on the principle of magnetic force restoration instead of the lever principle. The typical mechanism of such balances consists of electromagnetic servomotor generating a force counter the weight of a sample being measured. The main components of the servomotor are a permanent magnet producing a magnetic field and a coil supported by precision springs, which allows the coil to move in the direction of its axis. Since the direction of the current flowing in the coil and the direction of the radial magnetic field are perpendicular at all points, an electromagnetic force is exerted on the coil in the direction of its axis. This force is also applied on the sample placed on the balance pan mechanically coupled to the servomotor. An optical sensor detects the position of the coil and the sample, and provides a feedback or error signal to an electronic amplifier. When the weight of the sample and the electromagnetic force are balanced and the system is in equilibrium, the error detector is at the reference position or the null point. Then the average electric current in the servomotor coil is proportional to the electromagnetic force that is holding the sample with a given weight at the reference position. When the load applied by the sample changes, the motion of the coil is detected by the optical sensor providing the error signal, and the amplifier automatically adjusts the current to maintain the position of the coil at a reference position. The direction and magnitude of this current change are such as to restore the equilibrium condition. The electromagnetic force restoration system counters the weight exerted by the sample against the adjustable electromagnetic force exerted by the coil at a specific spatial position. By measuring the current in the coil and the electromagnetic force generated by it, we can determine the weight of the sample. Now we discuss the basic method of weighing and two other methods of double weighing. The basic method is single weighing with one stage, where the sample and the weights of known mass are balanced once. First we determine the equilibrium position x of the balance with empty pans in unloaded state. The length of left and right lever arms of the balance are denoted by L sub L and L sub R, whereas the position x is determined by the deflection angle phi of the pointer of the balance. We note that the deflection angle is not necessarily 0 for an unloaded balance. Then we place the sample of unknown mass m on one of the pans, for example on the left pan, and add a series of known weights of mass m sub r to the other pan such that the equilibrium position x of the balance could be restored. Here the subscript r indicates that the weights are placed on the right pan. Since we cannot generally combine the exact mass m sub r from a standard weigh set so that the perfect equilibrium position x could be restored even if we move the rider, we need to determine the mass m sub r by applying linear interpolation. Let us suppose that by using two different combinations of the series of weights of masses m sub 1 and m sub 2, we obtain the equilibrium position x sub 1 and x sub 2 with the original equilibrium position x between them. Then the linear interpolation gives the equation stating that the ratio of the difference between x and x sub 1 to the difference between x sub 2 and x sub 1, is equal to the ratio of the difference between m sub r and m sub 1 to the difference between m sub 2 and m sub 1. As a result, the mass m sub r can be approximated as m sub 1, plus the ratio of the difference between m sub 2 and m sub 1 to the difference between x sub 2 and x sub 1, times the difference between x and x sub 1. At the same time, the linear interpolation applied here also helps to determine the sensitivity of the balance for the given load as the ratio of the difference between x sub 2 and x sub 1 to the difference between m sub 2 and m sub 1. The torques produced by the weights of the central balance beam and the empty pans with respect to the point O of rotation cancel each other out in the equilibrium position x, and the net torque acting on the loaded balance vanishes in the same equilibrium position x as well, even if the lengths of lever arms are changed by the load. Then the net torque produced by the weight of the sample on the left pan and the weights of known mass on the right pan must also vanish, and the balance equation for this condition states the following. The mass m of the sample times the magnitude of the gravitational acceleration g times the length of the left lever arm L sub L times the cosine of the deflection angle phi, minus the mass m sub r of the weight on the right pan times the magnitude of the gravitational acceleration g times the length of the right lever arm L sub r times cosine phi is equal to 0. This equation gives the relation stating that the product of the mass m and the length L sub L is equal to the product of the mass m r and the length L sub r. As a result, the mass m of the sample can be expressed as the lever arm ratio, that is the ratio of the length L sub r of the right lever arm to the length L sub L of the left lever arm, times the total mass m sub r of the weights of known mass on the right pan. Generally, the mass m is not equal to the mass m sub r but proportional to it, where the proportionality constant is the lever arm ratio. However, we do not need to determine the lever arm ratio in many cases, for example when we prepare solutions where only the mass ratio of the components is needed. Now we discuss the methods of double weighing, or weighing of a load in two or more stages, where the sample and the weights of known mass are balanced twice or even more times. The first type of double weighing is known as Gauss's method, where the first stage of weighing seen in the first method is followed by a second stage with alternation of weights. That is, we interchange the role of the pans in the measurement by placing the sample onto the right pan and add weights of known mass to the left pan to restore the equilibrium state x obtained in the first stage of weighing. Generally, the mass m sub L of the weights on the left pan used to restore the balance is not exactly the same as the mass m sub r used in the first stage. Here the mass m sub r is also obtained by linear interpolation as seen in the first stage. Then we have two equations derived from the criterion of vanishing net torque in equilibrium for the two stages. For the first stage the original equation states that the mass m of the sample times the length L sub L of the left lever arm is equal to the mass m sub r times the length L sub r of the right lever arm. For the second stage we have the equation stating that the mass m times the length L sub r of the right lever arm is equal to the mass sub L times the length L sub L of the left lever arm. If we multiply the first equation by the second one, we can write that m squared times L sub L times L sub r is equal to m sub r times m sub L times L sub r times L sub L. Then the mass m of the sample can be written as the square root of the product of the mass m sub r and the mass m sub L, which is normally approximated as the average of the two masses. The lever arm ratio L sub L divided by L sub R can also be expressed from the ratio of the balance equations as the square root of the ratio of M sub R to M sub L. The second type of double weighing is called Borda's method, where the first stage of weighing is followed by substitution of weights, that is by replacing the sample with weights of equal total weight. In the first stage the sample of the unknown mass is placed in one of the pans, and balanced with fine shot or sand placed in the other. The equilibrium position does not need to be the same as the one for the unloaded balance. The sample is then replaced by known weights of the total mass m0 till the equilibrium position of the balance is again established. The mass m0 is generally obtained by linear interpolation as in the case of the single-stage weighing. Since the equilibrium position is the same for both the stages, the replacing weights represent the weight of the sample, that is the mass m is equal to the mass m0, regardless of the lever arm ratio of the balance. Let us consider various examples for weighing scales used in everyday life. We start with platform scales, which consist of a combination of levers so that the load on one lever becomes the effort that moves the next lever. This arrangement allows a small weight to balance a heavy load. In the schematic figure of a platform scale, the lever denoted by the letters A and C at its two ends is a first-kind lever with the fulcrum at the point O. A standard weight is suspended from its end A, whereas the second-kind lever denoted by the letters H and J is suspended from its end C. The fulcrum of the second-kind lever is at its end J. Another second-kind lever denoted by the letters D and E is suspended from the right arm of the first lever at the point B with its fulcrum at the end E at rest on the lever HJ. This lever serves as the platform of the scale on which the load can be applied. In this arrangement the following condition holds. The ratio of the distance OC to the distance OB is equal to the ratio of the distance JH to the distance JK. These ratios are constant, let us say n, even if the levers move. As a result, the platform has always a vertical displacement. For if the points B and D are lowered by the height h, then the points C and H are lowered by the height n times h, but the points K and E are lowered by the height h again. Now we can decompose the load G exerted on the platform into the parallel forces G1 and G2 acting at the points D and K, respectively. Since the line of action of the force G1 passes through the point B, we can translate the point of application of the force to the point B. By applying the lever principle, the force G2 can be replaced with the force G2 over n exerted at the point H with the lever arm n times longer than the one of the force G2. Here the force G divided by n can also be translated to the point C. If we apply the lever principle again, we can replace this force with the force n times G2 over n, that is the force G2 exerted at the point B with lever arm n times shorter than the one of the force acting at the point C. As a result, the net force applied at the point C is the vector sum of the forces G1 and G2, which is equal to the force G, regardless of where the load is placed on the platform, that is what the magnitudes of G1 and G2 are separately. In other words, we can consider the load placed on the platform as if it were suspended from the point B. Therefore, if the lever arm OA is 10 or 100 times longer than the lever arm OB, we are able to achieve balance between a body on the platform and a weight suspended from the point A that is 10 times or 100 times less than the load. After presenting scales used to weigh heavy objects, we can consider scales designed to measure the mass of very light bodies. Micro-weighing scales or microbalances operating on various principles are exceptionally precise instruments used for weighing very small samples with a high degree of accuracy. They have two basic components, electronics and another component containing the precision mechanical measuring cell. In quartz crystal microbalances, the cell has a quartz crystal, and the mass measurement is based on the observed changes to the resonance frequency of the crystal due to the addition of the sample. The cells in tapered element oscillating microbalances use a small vibrating gas tube measuring the mass concentration of aerosol particles, where the oscillation frequency of the tube changes when aerosol particles are deposited on it. Micro-weighing scales normally offer the maximum capacity between 1 mg and couple of hundred grams and readability or sensitivity down to 0.1 microgram. An important problem with high-resolution balances is related to the corrections of the buoyancy effects. The sample submerged in air is displacing air, which causes it to weigh less because the air is exerting an upward force on the sample equal to the amount air it displaced. Some microbalances offer an automatic air buoyancy correction software that ensures true mass measurement and compensation for fluctuations in air density. Another well-known example of scales is a trip scale used as a commercial weighing machine. It is an equal arm balance having pans which are flat platforms or shallow trays elevated above the beam. It has many different versions, such as the reverbal balance with two identical parallel beams mounted above a vertical column or two pivots placed in a case, as seen in the figure. On each side the horizontal beams are attached to vertical beams, and two horizontal plates are fixed on top of them. Since the vertical beams are always vertical and the plates are always horizontal, the mass of the sample placed on one of the plates is always equal to the mass of the calibrated weight added to the other plate, regardless of where the sample is placed on the plate. In the case of pendulum scales, for example the letter scale seen in the figure, the load is balanced by a pendulum moving from a vertical position representing the unload state, to a horizontal position representing the maximum weight measured by the scale. Here the torque produced by the load is in balance with the torque produced by a bob of the pendulum, where the mass of the load is determined by the position of the pendulum in the front of the calibrated scale seen on the round part of the device.